Have you ever been in a huge factory and seen one of those massive overhead cranes just gliding along, lifting tons and tons of material? It's pretty impressive. But what's actually holding that whole system up? Well, if you look closely, you'll see it's all resting on these tiny little concrete bits sticking out from the columns. So how can something so small handle so much weight and so much movement? Well, that's exactly what we're going to break down right now.
So here's our game plan. First, we'll get straight on what this thing actually is. Then, we'll dig into all the forces that are trying to rip it apart. After that, we'll look at the team of 3 steel reinforcements that keep it strong, we'll run through a real-world calculation, and then we'll wrap up with the final blueprint that brings it all together.
All right, let's dive right in. Before we can design one of these, we really need to understand what this unsung hero of structural engineering is all about and what its job is.
I mean, this is the fundamental question, right? It's not just about holding up something heavy. It's about supporting a dynamic system, something that's constantly starting, stopping, and moving huge loads around all day, every day. And the answer, well, it lies in this one little component.
And here it is. You might hear it called a short cantilever, or a corbel, or even a bracket. They all mean the exact same thing. Its entire reason for existing is to stick out from a column or a wall and create a solid seat for a really heavy, really concentrated load, just like the rail for that factory crane.
So now we know what it is, let's talk about what's trying to break it. And you might think, oh, it's just the weight pushing down, but it's actually way more complicated than that. Trust me, there is a lot more than just gravity going on here.
We're basically wrestling with 2 main forces. First, there's the obvious one, the vertical load, which we call V. That's just the raw weight of the crane and whatever it's carrying, pushing straight down. But the real troublemaker, the one that makes designing these tricky, is the horizontal load, or H. This is a sideways force, usually about 10% of the vertical load, and it's created every single time that crane speeds up, hits the brakes, or just jolts along its track. And this is a perfect way to picture it. You know when you're on a train and it starts or stops suddenly? You feel that lurch, right? That's the exact same idea here. The crane's wheels bumping and rolling along create those same jolts, and that generates a horizontal force that's literally trying to pull the cantilever straight off the column.
Okay, so we've got these forces trying to bend it, pull it, and shear it right off. So how do we fight back? Well, the answer is this really clever 3-part solution that uses different kinds of steel reinforcement, all working together as a team.
And here's our trio. You've got the main tension reinforcement. That's the real muscle. Then there's the shear friction reinforcement, which kind of acts like stitching. And finally, you have vertical stirrups for overall support. And each one has a very, very specific job to do.
Let's start with the big one, the main reinforcement. See, it's not just a straight piece of rebar, it's bent into this special fork shape. And that shape is absolutely critical because it has to do 2 jobs at once. It resists the bending force that's trying to snap the whole thing off, and it fights that horizontal force H that's trying to yank it away from the column.
All right, next up, the horizontal stirrups. Their job is to prevent something called shear friction failure. Just imagine that huge vertical load trying to slice the cantilever clean off the column, almost like a guillotine. Well, these horizontal bars act like internal stitches. They create friction and basically clamp the corbel to the column, stopping that catastrophic sliding failure from ever happening.
Okay, theory is great, but let's make this real. We're going to walk through an actual design example to see how we take all these ideas and turn them into hard numbers for a design that's both safe and efficient. All right, here's our setup. We've got a vertical load of 120 kilonewtons, and that means we have a horizontal load of 12 kilonewtons. The load itself is being applied 0.2 meters away from the column, and the corbel has an effective depth of 1.2 meters and a width of 0.3 meters. So let's see what kind of steel this is going to need. So the very first thing we have to do is calculate the total design moment, which we call M. This basically represents the total twisting force that our steel has to fight against. It's a combination of the vertical load times its distance and the horizontal load times its distance. And for our example, that comes out to 178 kilonewton meters. Now that we have that moment figured out, we can calculate the area of our main fork-shaped steel. This calculation takes care of both the bending and the direct pulling force. So we plug our numbers into the standard formulas, and we find out we need 1,443 square millimeters of steel.
Okay, next up, we calculate the steel we need to handle that shear friction we talked about, the horizontal stirrups. This is found by dividing our vertical force by the steel strength and a special friction coefficient. For this design, that gives us a requirement of 530 square millimeters of steel just for those stirrups.
Now, this is a super important point. In structural design, you always have to plan for the worst-case scenario. The main reinforcement has to pass multiple tests. We have to figure out the steel needed for bending and the steel needed for shear. And then, this is key, we have to choose the larger of those calculated areas. That's how we make sure the design is safe against everything.
We've run the numbers, but we are not done yet, not even close. The calculations mean absolutely nothing if the steel isn't put in the right place on the construction site. This final stage, called detailing, is where we draw up the blueprint for success.
And this blueprint has some rules you just can't break. For instance, that main fork-shaped bar has to extend deep into the column. We're talking at least 1.5 times its own length to get a proper grip. Those horizontal stirrups we calculated, they have to be packed into the top 2/3 of the core bowl, right where the highest stresses are. And for extra security, that main bar is often welded to a steel plate inside the column. These are the little details that make the whole thing work in the real world.
So there you have it. You've seen how this combination of force analysis, number crunching, and really careful detailing all come together to create this tiny but incredibly powerful component. It's really a testament to engineering precision. Which leaves me to one last question for you to think about. What do you think would happen if just one of these critical little details was missed?